Hello, my name is Ozgur Aydogan. Today I will talk about how to distinguish between real and imagined movements using brain signals. Overt factors such as our actual movement and proprioceptive input both notify and are informed by the covert processes of motor planning and movement preparation. ECoG recordings obtained by low-pass filtering of the brain signal recorded from a microelectrode placed in the cortex have increasing importance in cognitive and brain-machine interface studies. ECoG location at the surface of the brain affords a precise spatial and temporal resolution, making it ideal for BCIs. Therefore, this research allows us to understand better brain mechanism behind overt and imagery movement and can be used to improve future brain-computer interfaces. One critical aspect of movement-assistive brain-computer interfaces yet to be investigated is the delineation between neural activity associated with planning and overt movements or motor imagery. To investigate this issue, ECoG recordings from 7 epilepsy patients reviewed in the Mishra et al. 2010 article, providing unique access to neural activity were used. Raw data were used for features to be used in online brain-computer interfaces. Mishra has conducted trials with tongue or finger flexion movement, but only hand movement trials were used in this study. Since Mishra et al. Previously focused on the similarities of overt and imagery movement, the distinct features between these two were explored in this study. To highlight the differences of cortical activity between the overt and imagery blocks, the prefiltered data was used and a fast Fourier transform was performed on it to convert the time domain to frequency domain and looked at the power spectral density profiles of activity recorded from each electrode. Some obvious differences between these two were noted, and a support vector machine was created, which is a supervised learning model used for binary classification of two blocks. Then decoder accuracies were compared at different time windows of the 3000 milliseconds trial to understand when the difference between the overt and imagery arises. Here, an sample prior average spectral density of a channel of one subject is shown. Then in this channel, it is seen that there are different responses in the low or high frequency band. Therefore, the goal of the research is to try to train a classifier based on these features and see at what time point in a trial the most information can be obtained from the brain signal. Brain line represents overt data and the red line shows the imagery movement. Here, the mean decoding accuracy of the support vector machine is plotted as a function of time before and after stimulus onset. Accuracy before stimulus onset during the rest period provides the baseline level, and decoding accuracy is observed to increase at the onset of the stimulus. Therefore, neural activity in the first 1000 milliseconds during the motion planning is essential for distinguishing overt movement from motor imagery. Also, interestingly, after the first 500 milliseconds, during which the explicit movement must be performed, the decoding accuracy is not significantly different from the baseline level. This indicates that muscle activity is not a confusing variable to decode the images and over movement in our data. The summary, to classify the ECoG signal as either overt or emergent movement, a support vector machine classifier was implemented and two feature sets were compared. The first feature set is the power spectral density of the ECoG signal during movement planning, following the cue. The second feature is sliding windows of the prefiltered voltage during movement planning. It was seen that the power spectral density classifier performed better and detected the difference in spectral characteristics of the two modern types, motion types, with higher accuracy. As a result, neural activity associated with overt movement and motor imagery were successfully classified. And the applications, the intricacies of motor planning, motor imagery, and overt movement in relation to brain-machine interfaces can be made clear. And also, rehabilitation and assistive technologies can be created for those suffering from a variety of diseases and disabilities. Using healthy epilepsy patients as a starting point, assistive technologies can be adapted to meet the needs of individuals with problems affecting motor or brain function, such as stroke, spinal cord injury, cerebral palsy, and more. Thanks for watching. Feel free to reach us with these email addresses. Thanks for watching.